This is lecture 3 of our course EEE 4705. So in this lecture, we will try to understand some of the most frequently used instructions in 8051 assembly language. So these are jump, loop and call instructions. Here with different example, we will try to understand how these instructions work, how we can implement those in assembly language. And here also we are going to follow the first book here from Majidi, and maybe in some of the cases the second book will also help us. So first of all, let us start with a basic example of loop implemented using assembly language in 8051. Also here what we are trying to do is trying to do this arithmetic operation. 3 multiplied by 10 should be equal to 30, right? So how can we do that using assembly language? One idea is that we can just add 3 for 10 times, that will get us to 30, right? So we are going to basically do that. So how that happens, you can see that first of all we are moving the value 0 into register A, right? That is just basically clearing register A for our operation. Register A will save the value after each addition. So initially it will be 0, then it will be 3, then it will be 6. So in a loop it will just increment its value by 3 for 10 times, and at the end we are going to get 30. And then next line here, this R2 is basically will work as the counter here for that loop. How many times the loop should run, that will be actually controlled by this R2. Now one of the things we have to understand first for assembly language is, whenever we see this kind of labels and the code is getting executed line by line, at that moment the code or the system doesn't see the label. It is practically kind of invisible to them. So without looking at that, one by one the lines will be executed. But when we will get to this label, whenever in some of the line in the code itself, in the instruction itself, this label is being called, then we are going to get to that particular label, right? For example, I mean, if we talk about this particular instruction here, this one DZNZ, so this basically means decrement and jump if not 0. This is what basically means by DZNZ. So what will happen whenever we reach this line? At first, initially the register A or accumulator has 0 value stored inside of it, and 3 will be added with that in this particular line. This is our task, right? In each of the cases, whenever the loop runs, each time we want to add 3 with this register A. So that is done, and then this particular line is run, which is saying decrement R2 register and then jump if this R2 register is not equal to 0. Okay, so initially the value we have saved in R2 is 10, that will be decremented by 1. So currently the value should be 9. So understand, first of all we will decrement before the comparison. So first of all it will become 9, and then we will compare that value with the value of 0. And as these two are not equal, they are saying if not 0, if this R2 register is not equal to 0, then you can jump to this particular level again. So we will move to there. Okay, and if we go to this line again, this particular instruction will be executed. So previously the value of A was 3. Now with that another 3 will be added. So currently the value of register A should be 6. Again we will come here, again we will see that r2, what is the value of r2? Currently it should be 9, so decrement that by 1, so it will be 8, and compare that 8 with the value of 0, they are still not equal, so again they have to go, we have to go to this level again. So in this way again we are going to execute this line. It will happen up until we reach the value of 0 for r2, right? So in one of the cases what will happen, at the end, at some time we will see that we have reached here, the value of r2 is 1, and that will be decremented by 1, so the value should be 0 now, and then if we compare we will see the value is equal to 0. So at that moment we have fulfilled this condition, if not 0, right? If 0, basically not 0, if that is 0, then we don't have to go to this level particularly, we can go to the next line. So at that moment, after running this loop for multiple times, whenever r2 becomes 0, then we don't have to go to this level and we can move on to the next line. So in this way it works. So my question is, in this way how many times this loop can be run? Or if I want to clarify even more, our goal here is to complete this particular task here 10 times, right? This is our basic goal. So how many times this particular line or instruction will be executed in this particular code? So what we will see, starting from 10 to 9, 9 to 8, 8 to 7, in this way we will see 10 times this particular line will be executed, and starting from 0 we will see after 10 times the resultant value or the final value inside register A should be 30. And then what we do after the completion of loop, we will just put the value of A into register R5, right? So my question now is, if in this particular code we can run this particular loop 10 times, then using this kind of 8-bit registers like R2, R3 or whatever, what is the maximum number of times the loop in this program can be repeated? If I use R2, then what is the maximum number we can put here, and what is the maximum number of time this particular loop can be repeated with this kind of registers, right? So I think normal answer should be 255, because 8-bit register has the maximum value of what, 2 to the power 8 minus 1, so that is equal to 255. So the maximum value we can write or save inside of this kind of 8-bit registers is 255. So if you start from 255, this particular loop or this particular instruction also can be executed 255 times. But the correct answer should be actually 256, not 255. Why is that? So actually there is a special case or special trick we can use here. Because of that, we will see using this kind of registers, the maximum number for this loop is not 255, rather 256. So how that happens? Let's say if I write here 0 instead of 10, if I start with 0, then what will happen? So when initially this loop starts, whenever we reach this line for the first time, we are going to see that the value of R2 is equal to 0, and that will be decremented by 1 first, then it will be compared with 0, right? So whenever it is 0, it will be decremented by 1. So if 0 is reduced by 1, then what should be the result for this kind of 8-bit registers? That is the question, right? So how do we actually subtract values in binary arithmetic? So if we have R2, let's say R2, where this value is equal to 0 0 0 0 and 0 0 0 0, 8 bit. This is the initial value we have saved, and what we have to do, we have to actually subtract 1 from it, minus 1 basically. Or what we can do, we can just add minus 1 with this value, right? So basically first get the value of 1, then take 2's complement of 1. Whatever value we get, that should be added with this value of R2. The resultant value should be 1 less from 0. Okay, so let us try to do that. So first of all, I will write 1. So that will be in 8 bit 0 0 0 0 0 0 0 1. If you take 1's complement of that, 1's complement of this value, that will be what? All of them will be changed to 1 for this particular bit, and the last one will be 0. So 2's complement will be just add 1 with this value. So 1 1 1 1 1 1 1 1. So this is basically minus 1. Am I right? And what we have to do, we have to just add these two values, right? Add these two values. So if you add these two values, the result should be what? 1 1 1 1, and here also 1 1 1 1, which is equal to what? If H, or in decimal you can say 255. So you see, if you subtract 1 from 0, the result should be 255. So when you get to the loop for the first time, when you reach this line for the first moment, R2 initially will be 0, that will be decremented by 1, and the result should be 255, and 255 is not equal to 0, so we will have to go to again, and then it will be executed, right? And then we are going to see after that from 255 to 254, 254 to 253, in this way another 255 times this loop will be executed. So 255 plus 1 equals 256 times. So this is a special case basically, but in general you can understand the maximum number for this kind of 8-bit registers is 255. If we are talking about loop, what is the maximum value it should be? So the problem is, whenever we need a loop with higher number, okay, or let's say the same instructions we are trying to execute here, if I want to do that, if I want to run these instructions more than 255 or 256 times, then what should we do? How can we actually resolve that? For that we can try the same thing we have done for other programming language as well, loop inside a loop, nested loop, right? So here you can see an example like that. So our task here is to execute this line multiple times, which is actually, to be exact, 800 times we want to compute, right? Now how to do that? We're going to use two different counters here for two different loops. So you see this portion here, these two lines basically is the inner loop, and initially you have this particular value stored inside of register A, which is kind of interesting. Like 55H is basically like this: 0 1 0 1 0 1 0 1, and here the execution or the line we want to execute is CPLA, which means complement all the bits of register A. So if any bits of register A is 0, the result should be 1, and if any value is 1, that should be changed to 0. So basically complement all of the bits. So we are trying to do that. So that will be done, or that should be done 800 times here. And how we are doing that? With the help of these two particular registers. So you see we have two loops here. One of the loops is these two lines with again label, another one is these 4 lines basically, okay, with next label. So this is the inner loop, this is the outer loop. So how that happens? First of all, you see the R3 is loaded with 10, then R2 is loaded with 80 value, and when we reach here we will complement A. So if this value is 55H, after complements the result should be something like this, which is actually AAH. Okay, so that is what we are doing. After doing that, our counter is R2, which was initially loaded with 80. So we will come here, we will actually decrement that value by 1, so 79, and 79 is not equal to 0, so we have to go to again label. So we will come here, do this task again, or execute this line again, and again come here. So in this way this particular loop will be executed for 80 times. When you actually complete this loop for 80 times, then we are going to move on to this line, and here again we are going to see that R3, the current value is 10, that will be decremented by 1, so result is 9. 9 is not equal to 0, so we have to go to the label next. So we come here, we again load R2 with the value 80. So you see again we are reinitiating this particular inner loop, right? So each time we go here, we have to again run the inner loop for 80 times, and for this particular R3 the outer loop will be executed 10 times because R3 has 10. So you see the outer loop will be executing 10 times, and each time the outer loop runs, the inner loop has to run for 80 times. So in inner loop, this particular line which we want to execute will be run for 80 multiplied with 10, right? So 80 multiplied with 10, which is equal to 800 times. In this way, if we want to complete a particular task multiple times, we can use this kind of nested loops. Now like this, like here we are just trying to perform one task which is looping, but in assembly language this kind of instructions called DJNJ, these are actually called conditional jumps. So we are jumping from one place to another place based on our condition, whether that value is equal to 0 or not. Based on that we are jumping or not jumping. So these things are called conditional jumps, and later on we will see there are unconditional jumps where we don't need any kind of condition to fulfill for going to a particular level. If we just ask our program that you have to go to that level, you have to go to that level. So these are unconditional, but here we are just saying the conditional jumps, and we have multiple variants of this kind of conditional jumps. So we will see some of the examples here, like if we start with the first one, this is jump if 0. So what should be 0? So if register A or accumulator is equal to 0, then we will jump to a particular level. So you can see this kind of example. So at this moment we will just check register A. If the value of register A is equal to 0, we will go to the label instructed here. Okay, so you can make any label here you want, right? Like in the previous example we had labels like next, again. You can write your own label, no problem. Then the next one, jump if not 0, just opposite to the previous one, right? And DJNZ, I think we have already seen that, one example of that. And CJNE, this is quite important. So this means compare and jump if not equal. Okay, so let us look at one example that will be easier to understand. Like here you can see what we are doing some kind of comparison. So compare this particular register with this value. So if they are equal, that means if whatever stored in register A is equal to 65H, then we can move on to the next line without going to this level. But if they are not equal, then we have to go to the instructed level. So that's how it works. So also for this particular type of instructions, we have three possible ways to write this. The first one, as you can see, using one of them as register A, and another one is immediate value with hashtag. Another possibility is we can compare register A with a particular RAM location. So this is RAM location 40H. And also what we can do, we can use a register like R0 to R7, and another value should be immediate value with hashtag. So here for this particular one, if you use one of them as R0 to R7, this kind of registers, you cannot use RAM locations for the second one. So you cannot write an age, you have to use immediate value here. So these are the possible, so these are the three possible ways you can write CJNE. There are some other ones, maybe in the future lectures we will try to understand that, because we don't have enough knowledge right now to understand the syntax there. Okay, now let us come here, jump if carry. So here also we are talking about register A, and if any arithmetic happens, then if carry happens for register A, that will be detected by PSW register, and if that happens, then we have to jump basically. So you see the label is given here. If carry happens, we can just move on to the particular label instructed here, and JNC is jump if not carry, opposite to the previous one. So jump bit, jump not bit, these three are quite different compared to this one, in a sense that all the conditions are given based on 8-bit register or this kind of 8-bit values. But here these three are 1 bit, just talking about 1 bit. So jump if bit JB. So if the bit we are talking about is 1, then we will jump basically. So we use this kind of conditional jumps for pins of microcontroller ports. Like for our 8051 we have 4 ports, and for each of the ports we have 8 pins or 8 bits basically. So that I think in your lab experiments you have seen that the details of ports, like for example if we talk about port 1, for port 1 this is pin 0, right? In this way we can write up to 1.7. So we have port 0, port 1, port 2, port 3 for 8051, and for each of the ports we can have 8 different pins or 8 different bits, which starts from 0 up to 7. So here 1.0 up to 1.7, these are the possible 8 bits, and for port 3, 3.0 up to 3.7. So these are the 8 possibilities for port 3. So we are talking about just this pin. So this 1 bit can be either 1 or 0, and based on that we can go to the label or not. So these two are basically that. And the last one is exactly similar to this one, but after doing the comparison or looking at that whether the bit is 1 or 0, we are going to clear the bit. So let's say if the bit is 1, we are going to make it 0, and if the bit is 0, then still we are getting 0. It doesn't have to clear, it's already 0. Understand? But whatever the value we have for this particular bit, for this example, it will be compared with 1, whether this is 1 or not, and then we are going to clear that and go to the label based on the situation we have, whether this is 1 or 0. That's it. So now we will look at some examples of how we can use these conditional jumps in 8051 to complete different tasks, right? So we have taken one example from your Majidi book. So here we have to add multiple numbers, and whenever you are trying to add multiple numbers, the problem is you can look at here to understand, like here we will try to add 4 different numbers here, right? And if you add this 8-bit 4 different numbers, the result may not be within the 8-bit bounds. it can be 9 bit, it can be 10 bit, whatever. But the problem is the registers we use for this kind of arithmetic purposes, like register A, that is of 8 bits. So for doing the arithmetic addition, multiplication, whatever, if it goes beyond 8 bit, so to track that and also to save that, this is a difficult task, right? So how to actually do that? First of all, theoretically we will try to understand what happens, how can we detect that overflow, and how can we resolve that. That is the thing. So here we have 4 different numbers here, we will try to add them. So 2 at a time, we will add these two, the result will be here, then with that result we will add the third value, then there will be another result here, that value will be added with this one, right? So let us look at this result. So 1 0 equal to 1, 1 1 0, there's a carry 1 1 0, again carry 1 1 1, so 1 carry 1 1 0, carry 1 1 1, carry 1 1 0, carry 1 1 1. So the result should be what? 1 1. So as you can see, already we have an extra bit here, right? The result is 9 bit. Now with this result, let us try to add the second value. So 1 1 0, carry 1 1 0, carry 1 1 0, carry 1 1 1. So 1 carry 1 1 0, carry 1 1 1, 1 carry 1 1 0, carry 1 1 1. So 1 carry 1 1 0 1. So you see, this portion was extra here, here we have 2 bits extra. With that we will still try to add the result, right? So with the fourth number, let us try to add the result. So 0 1 1 1 1 1 1 0 1 1 1 0, carry 1 1 0, 1 1 1 1, carry 1 1 0, 1 1 1 1, carry 1, and we have this value 1. So here you see these two are actually adding together. So each time you add, you see you have this overflow happening here, here, and here, right? And what is happening each time, because this overflow is happening or carry is happening, this portion after 8 bit is getting increased by 1. So initially it was 1, then 1 0 is 2, and 1 1 is 3. So each time this overflow is happening or carry is happening, this upper portion after 8 bit is getting increased by 1. So what we can do, we can just detect whether carry happens, and if carry happens, we are going to increment these values and save it somewhere. That's the thing, to actually get the total result. So how we are going to do that? You know that to save this data or result, we need at least 2 registers, because each of the registers have maximum of 8 bits. So that means what we are going to do, we are going to take one of the registers of 8 bit to save the lower 8 bits, like we have here this portion. To do this, we are going to use one of the registers. Here it's actually written as R0, so we are going to use R0, and there will be another register used, 8 bit here, which is R5, which will actually keep the upper portion, the high bytes we have if carry happens. So what we are going to do, we are going to do the arithmetic on register A, obviously, and each time there is a carry, we are going to increment the value of R5 starting from 0. So 0 to 1 to 2 to 3. In this way, the upper bytes will be saved on R5 and lower bytes will be saved on register A. And after completing all of these additions, the result, this will be obviously be saved to A, and that will be moved to R0, because to save the lower 8 bits we have to use R0. So I mean, theoretically we have tried to explain that. To properly understand, let us look at the code. So here is the code we are going to use. So even though we have showed 4 different values in addition, here actually they are saying 3 values should be added, and actually initially we are storing the value 0 onto register A, basically clearing that out, and also we are clearing R5 to use that to store higher byte. So you can think of this particular portion as one of the additions, right? So you can put any value you want here so that we can add 4 different values. That is possible, but here initially that is taken as 0, so we don't have to worry about that. But what we're doing, we are trying to add 79H, this value, with whatever we have already saved in A, which is 0, and the result should be stored in again register A. The thing is, now after this addition, if any carry happens, we can detect that. That will be detected by the PSW register, right? One of the bit is particularly, detects the carry. So if that happens, this particular conditional jump will understand that. Okay, so jump if not carry. So jump if not carry means if carry doesn't happen in this particular arithmetic, then we are going to get to N1 label without executing this line. That is the idea. Okay, so if carry happens, we are going to increment the value of R5, so which is actually storing the higher bytes of our result, right? So if this is R5, it will store the higher bytes and the lower bytes will be saved by R0. So initially, currently A is doing its work, because after each arithmetic addition the result is saved on A, so we always have to do register A for arithmetic operations, and finally whatever we get, that will be saved onto or moved onto R0. Okay, so here we are trying to increment R5 whenever we see any carry happens after any kind of addition. Okay, so that happens. So if carry happens, then we are going to increment here, and if the carry doesn't happen, it will skip this line and go to this particular label and add the second line. And here also, if carry happens, we are going to increment here. We cannot skip this line, and if carry doesn't happen, we are going to move on to this particular label, skipping this line. So in this way, in 3 consecutive steps, we will add 3 different numbers with already whatever we have saved onto register A. And if carry happens, we are going to increment R5. If carry doesn't happen, we are going to skip that. And finally, after all the addition is done, you see we are actually moving whatever we have saved on A to R0, so that the lower 8 bits are saved by R0, and R5 will automatically increment whenever carry happens. So in that way, if we are talking about the previous condition we had for this one, for 3 of the times we are going to see carry happening, and R5 will increment by 1 for 3 times. Okay, so finally we are going to see 1 being saved onto R5, and lower 8 bits will be saved by R0. So in this way, using this conditional jump called jump if not carry, JNC, we can add multiple numbers, store the lower bytes on R0 or any kind of register, 8-bit register, and store the higher bytes on another registers. So in total we can have 16-bit result. Okay, so far we have talked about conditional jumps. Now we will talk about unconditional jumps. So unconditional jump is a particular type of jumps where we don't need any kind of condition to jump to a particular level. We unconditionally, we can move to a different location based on the instruction. So there are two types of jumps, basically unconditional jumps: long jump LJMP and short jump SJMP. The difference between these two is whenever we are talking about long jump, the instruction itself is 3 byte, and the first byte is opcode, and second third byte represent the 16-bit address of the target location. So let's say if I talk about the instruction, so let's say these 3 bytes are representing a long jump instruction. So the first one, this one will be opcode. So this is the first byte. The second and third, totally this thing will represent address. Okay, so basically ROM address. So wherever we are currently in the code, we have to jump to a particular location from that, right? So that particular location can be defined by an address, a ROM address, right? So that will be given by these 2 bytes, because we know for our 8051 the addresses, the length of addresses of ROM is 16-bit, so if we want to represent a full address to jump to a particular location, we have to use 16-bit or 2 byte basically. So that is done for long jump. So it is very easy to understand whenever we are converting that to machine language. So yeah, and obviously this is very easy to implement and easy to understand, because now because we have 2 byte for the memory address, we can locate anywhere from 0000 to FFFH address on the ROM. If our ROM has 64k bytes of memory, even then we can locate anywhere in there, no problem, with long jump instruction. Now the problem is whenever we started with this kind of 8051 microcontrollers, the problem is initially we never had this amount of memories, right? The original version had only 4k bytes of ROM, right? And in general we don't need that amount of ROM anyway. So if I have this kind of long jump instruction, we may never need to access that total 64k bytes of memory. It is just unnecessary. Another thing is, if I want to write long jump, I have to use 3 bytes. So whenever you have 4k bytes of memory in there, every byte is precious, because you are writing a program, it will take or consume memory. So the idea was, can we actually make it more efficient? For that we have another command or instruction called short jump, which is just shorter version of long jump. And instead of 3 bytes for this short jump, we have 2 bytes. The first byte is always the opcode, so specifically just denoting what instruction is that. For the next byte, the 8-bit, that will actually denote the relative address of the target location. So what is relative address, we will try to understand very soon, but you have to understand, instead of 2 byte, now we have only 1 byte of space to represent the location, right? Location of the memory. So we have to somehow take some intelligent approach so that we can identify different location and move to different locations using this 1 byte 8-bit space. So how that is done, we will try to understand very soon. But Another thing I will try to mention here, which is important if we want to understand the next page, is all the conditional jumps we have talked about previously, the loops and all other conditional jumps. They are actually sort of like short jumps in their behavior, in their structure of machine code. Like they are also 2 byte. Also, for conditional jumps, the first byte will be designated for the opcode, and the next byte will be the relative address basically of the target location. So what is relative address, and how can we actually understand that? What you have to understand, like here using this example, I will try to explain what is relative address and how it can actually help us to get to the target location. Now, one of the thing is, what you have to understand is three things. First thing, current PC value. Okay. Another thing is relative address. And the last one is target address, right? Okay. So what is current PC value? PC means program counter, right? So each time you are executing a line, so what should be the value of program counter, right? That is the question. So here in this example, we have this assembly code, and with that, if that gets converted into its machine code version, this will be the representation, and in which address, ROM address, each of the lines are stored, that is also shown here. From that, we will try to understand how we can go to a particular target location, right? Now the thing is, what you have to understand, whenever we are executing a particular line, let's say we are executing this line 3, right? Now at this moment, what should be the value of program counter? So we always say program counter always points to the next instruction to be fetched. So program counter will store the address of the next instruction to be fetched. So at this moment, if we are talking about this line, we are executing this line, program counter will store the address of the next instruction, which is this one. So at this particular line, if we are executing this line right now, the value of PC is this one, 0004. Understand? With respect to this PC value currently we have, relatively how far our target address is, that will be actually denoted by this relative address. So either it can be in forward direction or reverse direction. Okay, so based on that, current PC value, with that we are going to add or subtract this relative address, and we are going to get a target address that is either in forward direction or in reverse direction. Now one of the thing is, you have to understand, because we said in the last page, in total short jump is 2 byte instruction, first byte is opcode, and second byte only 8 bit is dedicated for relative address, right? So that means that 8 bit can represent maximum of what, 2 to the power 8, which is 255. 0 to 255 is the maximum range. So what you can do, either you can make a situation that from the location you are currently in, you can move forward to 255 lines forward. You can do that, but in reverse direction you have no scope to go, right? That is not very useful. So we may have to go forward, may have to go backward. In most of the loops we have seen, we go backward. So how to resolve that? So what we do, we actually divide these possibilities we have into two portions. So basically in the forward direction we can go 127 lines basically, or 127 bytes, and in backward direction we can go 128 bytes, right? So this can be denoted by minus because we are in reverse direction, right? Now with one or two example we will try to understand in this code how in all the conditional jumps or these short jumps how this relative address is written so that we can move on to the target address. So let us try to understand. So you see, let us look at two conditional jumps, like jump if 0 and another one is jump if not carry. Okay, so first let us look at jump 0. So here they are saying if the condition is fulfilled they have to go to the label next, which is here, right, in this particular line. Now here this is the machine code for this particular instruction, and the 60 here, this is the opcode, and 03 is the relative address from the information we had from earlier, right? And what we're going to do, we are going to add this relative address with the current PC value. So program counter currently, if we are in this line, what should be the current value of program counter? The next address value, right? So this is that. So 0006. So we are going to take just the last 8 bits of this address, because all the things we will calculate will be in terms of 8 bit. Okay, so this one was 8 bit. So also from this current PC value or the address of the next instruction, we will take 06. So 06 is current PC, right? So if you add these two, you are going to get the target address. So let us try to see if that is correct. So if you go to 0009, this address, yes, this is the label next where we need to go, right? Understand, right? So in this way we can actually calculate. Now let us look at another example of this one, right? Jump if not carry. So here also what we will do, we will first look at the value of current PC. Program counter currently holds the value, this one, so 0 0 0 D, and with that we will try to add the last 8 bits of our instruction. So 50 is the opcode and 05 is the relative address. So let us try to add that relative address and add these two, right? And also we can just forget about this upper bytes and add these two. If you add these two, you are going to see that the result is equal to 1 2 in hexadecimal. So both of them are actually hexadecimal value, remember that. So result value is also hexadecimal and the value is 12, and it's saying if the condition is fulfilled we have to go to the label over, and if you look at this over label, it has the address of 0012. So you understand, right? So in this way we can actually, using relative address, go to the target address of our label. Now let us try to look two more examples. So we will look at this one, jump if not carry again. Okay, and previous two examples were jump in forward direction, this will be in reverse direction, right? Like here we have again here, try to find out the relative address and also the current program counter value. So in this particular line, the current program counter value should be what? This one. So 0015, we will take just 15. This is the current PC. Okay. And here the last 8 bit is the relative address. So F2 relative, and if you add these two, you are going to get what? The target address. So if you add these two, you are going to see that the result is showing as 107, which should be the target address. The thing is, here also you can see we have to omit this value 1 because we are only calculating in terms of 8 bits. So anything that comes after 8 bit is overflow and can be omitted. So if you omit this portion, you have 07, which should be the target address, or also we can say 0007 because our addresses are of 16 bits. So if you look at 007, you see we have again label in backward direction, right? Now last example, so we will try to calculate for this one. So we have a short jump and how to actually calculate the relative address and target address for this one. So for this one, the current PC value is this one, right? 0017. So we will just take 17, and from this one the last 8 bit is the relative address. So FE, all of them are hexadecimal values, and if you add these two, let us add these two, the result should be 115 in hexadecimal. Okay, so again here also we can omit this one and we can only just consider this 15, and we can put 2 zeros here. That should be the target address. So if that is the case, this is the line we again go back to. So you see the label is actually in this line, so we have to go back to this line, infinite loop, right? So this also proves our theory, right? So another question that can be like in the backward direction, how it actually works. So you see we have added a value with 17 and we have gotten a lower value somehow, right? I mean, we had a carry or overflow, but we could omit that by the law of binary addition. So finally we got the result which is less than the initial value we had. So how it actually works? So it happens with the help of 2's complement addition and subtraction logic. So if you look at this particular value, which is FEH in hexadecimal, right? So FE, if you take the equivalent binary, it should be what? 1111 and 1110. Am I right? So if you take the 2's complement of that, that will be what? First take the 1's complement. So 0 0 0 0 0 0 0 1, and if you take the 2's complement, then what? It will be 0 0 0 0 0 0 1 0. So which is equal to what? 2 in decimal. Am I right? So if you have started with this value and taken the 2's complement of that, and finally that resulted into a value of 2 plus 2, then obviously this value should be minus 2, right? So actually what we did is added 17 with minus 2, and because of that we have got plus 15 as result. Understand? So for both of the cases, the last two examples we have seen, for this one and also this one, we are going backward, and what we are actually doing, we are actually subtracting this f2 is a 2's complement value of a positive value, and f is a 2's complement value of a positive value, right? So in this way we are actually subtracting from the current program counter value we have, so that we can go in backward direction. But you have to understand, because we have maximum of 8 bits for relative address, for representing relative address, that's why in forward direction we can go 127 locations at maximum of ROM, and in backward it should be 128 locations, or 128 bytes you can say, because each of the locations can have 8 bits of storage. Okay, now let us talk about call instructions. So call instructions are used to call subroutines. If you want to understand what subroutine is, it is just like functions as you have seen in C programming or Python. So basically whenever we have a particular lines of instruction or tasks to be completed frequently, what we do, we write a function for that, and whenever we need we can just call that easily without writing the whole code again and again. So subroutines are basically that. For assembly language specifically this term is mostly used, but generally functions and subroutines are almost same. And for 8051, for this assembly language, we have two different calls called L call or long call, and another one is A call or absolute call. So first of all we will talk about L call, long call. So this one is 3 byte instructions. First byte is opcode as always, and second and third bytes, so in total 16 bit is actually used for the address of the target subroutine. So you are going to see that like if I want to give you an example of call instructions, like here you can see we have L call delay. So we are calling a particular label, and that label basically is the starting location of the subroutine. So here this one is the subroutine we are talking about, starting from 300H location. So this particular portion up to this return, this portion is the subroutine, and we will try to call that using this particular command called lcall and then that label. Okay, understand? Now here you see the first byte is the opcode, and second and third bytes are used for the address of the target subroutine. So you have to actually get to that particular location, for our case which is 300H location, right? So you have to somehow give the address to your command of that target subroutine, the starting location of the target subroutine. That is done using the second and third bytes of the instruction. So as you have 16 bit available for giving that address, you can access anywhere from 0 up to 64k bytes of memory of your ROM. There is no problem, right? Not like your short jump where we have some limitation, we have to use relative address to address that. So one thing you have to understand, like in the previous code we will look at this particular code deeply and understand, but understand that whenever we are calling this particular subroutine delay, it can go there and execute everything whatever is called, but after completing that you have to again come back here. I mean, you have to come back to the next line. You have completed this command, so whenever you return from here after getting this RET, you have to return to the next line here. So how it does that, how it will actually remember that previously it was in this line and now it has to be here? For that we have a special method basically inside of 8051. So whenever this kind of subroutines get called using lcall or acall, whatever, first of all processor will automatically push the current program counter value onto the stack, right? First of all it will do that. So on the stack we will have some value, and then it will go to the starting address of the subroutine and starts fetching the instruction from there, basically executing everything After completing the subroutine, execution of the subroutine is completed, then what will happen? We will reach ret or return command or instruction, right? If that happens, this will basically pop the saved address from the stack onto the program counter. Okay, so initially when we started with the subroutine, what we did, we actually saved the current program counter value onto the stack, because that is where we have to return to. We will try to understand, we will understand in detail in the next example, in the next page, but try to understand that will be saved onto the stack whenever we are going to the subroutine, and whenever we are reaching the RET, that address will be again popped to the program counter, so that from the next location after the call instruction, from there we can start again executing everything, because we have to return at some point when we reach or see the return command ret. Okay, so if you don't understand right now, let us look at this example. Now it will be very easy to understand. Okay, so here this is the line where we are calling a subroutine, right? And subroutine starts from here, from 300h location. So whenever we are actually calling that, we have to understand what is the current program counter value at this line. So whenever you are in this line, the current program counter value is the next instruction address, right? The starting address of the next instruction, so 0007. That value will be automatically pushed onto the stack. So here we have this stack. So because we have 2 bytes to save, that's why we will need 2 locations. So in 08 location, we will have the lower byte of the address, and higher byte will be saved onto 09 location, and stack pointer will have 09h value, right? So that will happen, and then it will go to here, execute everything. So we have a delay routine to complete. After completing that, it will reach here, this return command. Whenever it reaches return command, this data we have saved onto stack, it will be popped, and it will be popped onto program counter. So whatever value we have currently saved on program counter, that will obviously be a address, right? Any instruction to be faced, that address is actually saved here, that will be overwritten by this particular address, so 0007, that will be saved onto the program counter. And because of that, it will understand I have to start executing from this line, because program counter always guides the processor to execute line by line what commands or what instructions we have to execute, right? So as we are changing the value of program counter, instead of executing anything here, it will return here and start executing from here similarly. Okay, so in this way, this basically helps, and stack pointer and stack helps to that. Now let us look at another example of call instruction. Here we will understand why we have to be very careful of using stacks whenever we are inside of a subroutine, because when we are inside a subroutine, already the stack has stored the saved address where we need to return to after we have completed the subroutine, right? So if you try to manipulate that stack using push and pop, there can be problems, right? You may not get the exact address you want whenever you have reached return ret, right? So basically how that happens and what should we do in these cases. So in this example, if you try to understand, you will see that here what we are trying to do is we are trying to first of all save some data onto R5 and R4 here, right? And then we will call a subroutine delay, right? This is the subroutine. Here you can see the issue is we are using the same registers R4 and R5 for the loops we are using here. You see, you have two different loops here, the inner loop and the outer loop, but for both of them the counters we are using are of R4 and R5, right? Both of them have 255 value. Now whenever you are actually returning into the code, you should have these values saved, not the values from here. But whenever you are going to the delay subroutine, obviously these values will can get overwritten by these values, and then we may never get that value which we need whenever we return to this particular location again. The R4 and R5 should have this value and this value saved. So how to actually resolve that issue? So if we can use push and pop, maybe we can resolve that. So how to do that? Initially from here, let us start. Like we have this value, we are trying to move that value to our port 1, then we have moved these two values onto R4 and R5, then we have called the delay. So if you come here in delay, which starts from 300H locations. Another thing I have to also mention, like look at the code here. I think I forgot to mention that, but this is 3-byte instructions. This is the machine code of the assembly language. So this is 3-byte instruction, and the first byte is denoting the type of code, opcode, and next 2 bytes, these 16 bits are giving us the target address. Okay, so target address should be what? 300H or 0300. So that is actually written here, right? So for lcall, this should be the general format, 3 bytes instruction. And from the previous discussion, we said that yeah, these two are the registers saving these two values, and we have come to here. So before overwriting R4 and R5, first of all we have to somehow save the values of R4 and R5. So how we are going to do that? Using the stack. So when you just executed this line, you have executed this line and come to here in this delay, you are going to see already you have the current program counter value saved onto the stack. So current program counter value should be what? This one, the address of the next instruction, which is 000B. Lower byte is saved onto 08 and higher byte is saved onto 09 location of RAM, right? And after that we will go here, and if you go here you will see that we have instruction push 4. So whatever we have saved onto R4, that will be pushed onto stack. Okay, so push 4 means whatever you have saved onto R4, that will be pushed onto the stack, and that is what happened, right? Now this 99 value was pushed from R4 into the stack, actually occupying the space 0A RAM location, right? And in the next one, if I go to the next line, now you see the next value, next position is filled by 67, which is the value of R5, because we have written push 5. So whatever you have stored inside of R5, that should be pushed onto the stack. So now 0B location is occupying and storing the value of R5. Okay, and accordingly you see the stack pointer was also being incremented, right? Now let us look at the next portions. Like here, now we can move any values we want onto R5 and R4, because already we have pushed the values of R4 and R5 onto the stack, and whenever we need we can again pop those. So now these values are getting overwritten by 255 or FFH, because this will be used as counter for our loop. So R5 gets this value, then we have this loop which will run for 255 times, and the outer loop, this also have 255 value, so this will also run for 255 times. So after getting all this done, we will reach here, right? So if you reach here, you see now pop 5 means whatever value we have at the top of the stack, that will be moved on to R5. Understand? So pop 5 means whatever you have on the top of the stack, which was what, which was 67 from previous line. So that 67 will be popped onto R5. So R5 currently has 67 value, and if you go to the next line, this 99 value, this will be popped onto R4. So you see, this is getting blank, and R4 currently has 99 value. So which is what we need, because initially we started with R4 to be 99H and R5 was 67H. So after completing our task, we have to again give the values we taken from R4 and R5. So we have done those, and then finally we can reach return. And if you go to return, obviously the address we have, the program counter value we had saved when we came to this subroutine, that will be popped from here and gone to the program counter. So if you do that, you see now the program counter has 000B as value, and because of that, now our instructions will start execution from this particular line, right? Because the program counter points to that particular location. In this way it will work. Now what you have to understand here, the number of pushes and number of pops inside of the subroutine is equal. If that happens, then there will be no problem for this kind of call instructions. So there will be no issue in the stack, because if let's say you have done 3 pushes and 2 pops, there will be still one value stored on top of stack that is not the address. Because of that, whenever you are actually returning, you are not getting the exact address or where you should be returning to. That is the problem. Understand? So the number of pushes and number of pops should be equal whenever inside the subroutine. Now a call or absolute call. So this is kind of like your short jump situation. So for efficient operation, we have another instruction so that we don't need to use the 3 bytes of just like L call. So this is 2 byte instruction, and one of the things which is quite weird here is not the full byte of the first byte is used for opcode, rather only 5 bits of the first byte will be used for the opcode, and 3 bits of the first byte and the total second byte, which is 8 bit, right? So 3 bits plus 8 bits, these total 11 bits are for the address. So basically what you can address is in total 2 to the power 11 or what, 2k. Okay, so 2k locations or 2k bytes, whatever you say. So what happens basically is, whenever you have a call, you can think of your ROM as combination of multiple memory blocks. Okay, so let's say you have 64k bytes of memory. You can actually divide those into 32 different memory blocks, something like this, maybe up to the last one. Okay, and each of them, let's say, have 2k bytes of memory. So if you divide them like that, so you can have 0, 1, 2 in this way up to 31. So in total 32 different memory blocks. So we are talking about this kind of memory blocks, and whenever your current instruction is inside of one of the blocks, so what they're trying to tell is the subroutine should also be in that particular memory block, otherwise there will be problem. Because how absolute call works is, because you have only 11 bits to represent the address or the target address, so these 11 bits, so basically let us represent total 16 bit address. So a call can only represent the 8 bits here, 8, and from there only 3, right? So this is 3. So the other 5 will be coming from program counter. Okay, so currently in the line we are in, the current instruction, based on that the current program counter will have some value, the total 16 bits. So the first 5 bits or most significant 5 bits will be taken from PC, and the last 11 bits will be coming from our absolute call. So because of that, we have to be in the same 2K region, because that will be based on the 5 bits of PC. Because if this is 5 bits, in total there can be 2 to the power 5 or 32 combination. So those 32 combinations we are talking about here. So we have to be very careful about that. We have to be in the same 2K region as the current instruction, otherwise there will be problem. And that's why most of the cases A call is avoided, L call is mostly preferred. But as you can see, A call is most efficient because it is taking less amount of memory, but you have to be careful, that's the thing. Now here we will try to learn how to calculate the time for the delays. I think you have seen a lot of delays in your lab experiments, but how to exactly calculate the accurate time of the delays we are giving there, we will try to understand that here. To understand that, one of the concepts that needs to be understood is machine cycle. So it is kind of like your states in SAP 1, if you remember. So in our SAP 1 we had 2 tasks, like fetch the code, then execute the code. Each of the instructions were executed like that, but also we saw that we had 6 different states in each of the instructions, right? So similar kind of concept you can say here, but slightly different. But all of the things happen because of clock pulse. This is the unit of time basically for our machine. So crystal oscillators basically does that, attached to our microcontroller. So each complete oscillation of the clock source is called clock pulse, like we can see here. This is the unit of time, as I had said. But 2 such pulses will produce a state for 8051. So something like that. You can see this particular portion here, this is 1 clock pulse. 2 such things will produce a state. 6 such states will generate 1 machine cycle. So this is what machine cycle is. Or also we can say 12 clock pulses will generate 1 machine cycle for 8051. For any instructions, we will see that 8051 may need 1, 2 or 4 such machine cycles. So it can vary based on the instruction. Some of the instructions may take 1 machine cycle, some of the instructions may take 2, some of them can take 4. So in this way, but all of the things are defined based on machine cycle. And we will try to also calculate what is the amount of time for each of the machine cycles for a particular version of 8051, right? So let us try to do that. But before that, another important thing is the frequency of oscillation we have. Like as we said earlier, crystal oscillator or different sources can be there for giving the clock pulse. Generally, most of the cases we use crystal oscillator for our microcontrollers. Also, another thing is based on the microcontroller we have, there is a minimum and maximum clock frequency that it allows. We know that from lecture 1 maybe. We have to be within that region. Generally, most of the cases you are going to see that 12 megahertz is a very common practice for 8051 to be used. And another one is this value 11.0592. This megahertz is mostly used whenever we are trying to maintain serial communications with computer or something like that. Will be discussed in future, this kind of things, why we use this kind of frequency, why this is useful, because of the baud rate and this kind of things. We will discuss that in future lectures, but for now you will see that in our math problems or any kind of code problems, if you are told to calculate the amount of time for a particular code execution, mostly these values will come up, either a frequency of 12 megahertz or 11.0592. Okay. Now let us look at one example to understand how to calculate the machine cycle for different frequency used in 8051. So here, as you can see, for this one, what you have to do is, we already know for 8051 based systems, like for example 8089C51 or 52, so this one is used in your lab. So for this kind of microcontrollers, if you want to calculate the time for one machine cycle, then how to do that? First of all, from the frequency you have to calculate the time period of one clock cycle, right? So that will be found out by inversing the frequency. So if you inverse the value, you're going to get 0.090422 microsecond, right? And because we know 12 such clock pulses will give us one machine cycle, so we can multiply with 12 and you are going to get something like this, 1.085 microsecond. So for this kind of system, one machine cycle is equal to this amount of time. Okay, for this one you can do the same thing. 1 divided f is the time period, so which is 0.0625 microsecond. You have to multiply it with 12. You are going to get the length of one machine cycle, so 0.75 microsecond. So here I will add 12 megahertz instead of 20 because this is mostly used, so it will be helpful whenever we try to solve another problem from 12 megahertz. So for 12 megahertz, the length of one time period will be what? 1 by 12 microsecond, and if you multiply that with 12, you are going to get what? 1 microsecond, right? So for 12 megahertz system, 1 microsecond is the length of one machine cycle. Okay, now let us look at some of the instructions and how many machine cycles are needed to execute that instruction. Okay, so here just some common instructions are given, like if you give any kind of move instruction, machine cycle, we need one machine cycle to complete that. For long jump and short jump, we need two machine cycle, and because we are talking about a system with 11.0592 megahertz, that's why the length of one machine cycle is equal to 1.085 microseconds. So that's why we are just multiplying with that and we are getting the. So one of the things you have to, you can see here is multiplication takes more time. So you see 4 machine cycles and as a result more time to execute. And these are just some of the examples, some common examples of instructions and number of machine cycles, amount of time taken to execute. But if you want to look at the whole table of all the instructions and how many machine cycles are needed to complete them, you can look at appendix A of your Majidi book, and there table A1 basically denotes all of them. You can look at them, and most probably in your exam I will put the table as a supplementary material for your questions, so that you don't have to remember the machine cycles for each of the instructions. You can just use them to calculate. Okay, so let us look at one simple examples of how to calculate the time delay, exact time delay for any kind of code, right? So we are taking one example from Majidi book 315. So here you can see 8051 system with 11.0592 megahertz. So they are telling what should be the time delay, basically what is the amount of time we are getting from that delay. So here you see this is the program, and but here we have used a subroutine delay, and we have to calculate how much time we are getting from this delay. So in this delay subroutine, first of all, using the help of that appendix table which will be given to your exam, so we can find out for each of the instruction how many machine cycles are needed to complete. For any kind of move instruction, we know 1. For this instruction, 2 machine cycle, and rate instruction takes 2. So for this particular code, you understand in this particular line, this is a loop, and initially you are loaded with 200 value onto R3, and this is get decremented and compared, then you are getting to this here loop. In this way it will continue in a loop. How many times? 200 times. So this particular line will be executed 200 times. So here this is written 200 multiplied with 2, and with that we also have rate instruction and this line. These two lines will be executed only once. Okay, so when we are starting here, once this line will be executed, then we are getting here this line will be executed for 200 times, because this is a loop and R3 has initial value as 200. But after completing this line for 200 times, we are going to get rate and then go to this next line after completing this line, right? So in this way it will happen. So that's why it's written like this. This is for the middle line, this is for the first line, and this is for the last line. So this is the total, and for this is the amount of machine cycles needed, total machine cycles needed for completing this instruction, right? Completing this subroutine. And for each of the machine cycles for this kind of systems, we have 1.085 microsecond time for machine cycle, right? So if you multiply that with this value, you are going to get the result. So very simple to understand, right? So before we move on to the next problem, we should discuss about one thing, like in your book in page 84, they have talked about different versions of 8051 microcontrollers, where number of clock pulse per machine cycle is different. Like if we talk about TS5000 microcontroller, the number of clocks per machine cycle is 4. Or if we talk about DS89C 420, 430, 440, 450, this kind of microcontrollers have 1 clock pulse per 1 machine cycle. So different compared to what we have discussed. So we don't have to worry about those, or we don't have to do any kind of calculations that are related to those. Like for example, example 319, 3.19, 3.20 and 3.22, these are done for DS89C 420. We can avoid those. We don't have to calculate those. We just have to understand the concept, which will be done through this basic 8051 system, where we have 12 clock pulse per 1 machine cycle. Basically we are talking about this kind of models: 80, 89, C, 51 or 52, or this kind of system where 12 clock pulses equal to 1 machine cycle. Okay, so all of the problems we will give in the exam will be based on this one. So whenever we are saying this one, we can just assume that 12 clock pulse is equal to 1 machine cycle, or whatever we have discussed so far, these are based on the same type of systems. Okay, so here let us look at another problem. Let's say we want to have the same kind of delay like we have in the last one, but we want to increase the amount of time for the delay. How can we do that? We have an instruction called NOP, no operation, where nothing is done, nothing is executed, but some amount of time is basically spent, so which is equal to 1 machine cycle. So you can just put the multiple nope here with our loop inside of this loop, so that we can add those onto our delay. So what is happening here, our loop is from here to here, right? So whenever you are initially loading R3 with 250, after that this particular portion, this loop will be executed for 250 times, and in this portion we have 1 plus 1 plus 1 plus 1 plus 2. So 1 plus 1 plus 1 plus 1 plus 2. This amount of times are needed if this loop is executed for once, and this will be executed for 250 times. So that's why we can multiply with 250. That will get us the total number of machine cycles inside of the loop. Okay, that will be multiplied with the time taken for each machine cycle, which is 1.085 microsecond for this kind of systems. You get the value, the time delay inside of the loop. With that you have to add this one and this one, right? So that is done here. This one is the external delay, external to the actual delay, basically, you know. So you add that, you get the total delay. Very simple to understand. Now next, one other problem here, similar to other ones, but here we have nested loops. So loop inside a loop, how can we calculate that? So we have to start from the inner loop, then we can move on to the outer ones. So the inner one is this one, basically, right? This here loop, we have to calculate the delay for that. In total 1 plus 1 plus 2, 4 machine cycles if we try to execute this particular loop once, and we have to execute this loop for how many times? 250 times, because R3 is loaded with 250. So that is what done. You see 4 with 250 multiplied, and the amount of time for each machine cycle, you get the value, right? Then what you can do with that, or with this is the amount of machine cycles done inside of this loop, 1000, right? With that, this amount of time will be added if we are talking about the outer loop. Again one, right? This one we are talking about. Here on top of the inner loop we have this portion, so we will add this portion, which is 4 multiplied with 250, which is 1000. We have written 1000, and with that this 1 and 2 will be added. So we have added this portion, and this whole thing, whatever we are seeing, this will be executed for how many times? 200 times, because the R2, which is counting the outer loop, was loaded with 200 initially, so that will be run for 200 times, and this is the total amount of machine cycles by the outer loop again, right? This amount of code is actually giving us this amount of machine cycles, and you multiply with this value, you get the total amount of time, right? And with that also we have to add this one and this one. So 3 machine cycles outside the loop, 3 machine cycles is added here with the inner machine cycles, and you get the total amount of time. Okay, another thing I have to mention, like in your book there are some assumptions made that you can just omit some portion, like you can just omit this 1 and 2, because if you omit these two, still the delay is almost same. So somehow sometimes we can approximate our delay calculation, still we are getting almost the same value. So in your exam, try to avoid that concept, okay? Try to avoid that approach, because you have to accurately calculate whatever you are asked. Like if I'm asking how much delay you are getting here, you have to accurately calculate, and you cannot approximate anywhere. What you can approximate is in this kind of problems, like here they are asking us to write a program to toggle all the bits of port 1 every 200 milliseconds. That means you have to create a delay for 200 milliseconds. So exactly accurately making 200 millisecond may not be possible, so you can approximate that, but your result should be very close to 200 milliseconds. So error that can be tolerated for these cases can be something like 0.5%, okay? So it should be almost accurate to this one, okay? But exactly 200 millisecond delay, to create that, it may not be possible. So I can consider in these cases. But if we talk about this kind of problems here, if we are asking you to calculate the amount of delay or amount of time taken for this execution, you have to calculate everything, you cannot approximate anywhere. Now let us look at this problem. Like here they are saying write a program to toggle all the bits of port 1 every 200 millisecond. So what do we mean by toggling? Like if we talk about port 1, we have 8 different pins, right? So P, so basically if I say this is P1.7, then this is P1.0, right? And toggling means maybe we can start with the value 0 1 0 1 0 1 0 1, which is 55, right? And then toggling means what? 1 0 1 0 1 0 1 0 AAH. Or also we can take the approach we have taken here. So in this example, you see initially we have started with 55H, which is the value here, and then we have actually moved this value of A onto our port port 1, and we have called the delay, which should be 200 millisecond. Then we have used CPLA, so we have complemented all the bits of A, and then we have short jumped again, so it will come here and complemented value is already saved on to A, so that will be moved on to P1. So in this way, after 200 millisecond, all the bits will be toggled. Now let us look at the delay portion, okay? So how it actually works and what is the amount of time we are getting from this delay. It should be 200 millisecond, right? So let us try to look at that. So in this code, we have used a nested loop of 3 different layers. So one of the layers is this one, just this one, right? This is the inner loop. Then we have this loop here 2, and then we have here 3. Am I right? So you can start with the inner one. Inner one takes what? 2 multiplied with 255. So 2 multiplied with 255, this is the amount of machine cycles taken by the inner loop, here 3, and you get the amount of time. Then we can look at here 2, this one, right? And for this one, we will add these machine cycles with the outer portion. So this portion and that portion, you add these two, you are going to get the total amount of machine cycles you are going to spend for one loop of here 2 loop, okay? So this one, and this loop is being executed for what? 195, getting looped for 195 times. So you multiply that with the amount of time taken for each machine cycle, because we are talking about a microcontroller with 12 megahertz clock frequency. So that's why this is 1 microsecond, not 1.085. You are getting this value. Then we can go to the outer one. So this one basically now. So whatever machine cycles you get from this one, which is, you add all of them together, you get the total result here, you put it here, and then with that you have to add this one and this one, right? And you do this, and this is the total amount of machine cycles if you execute the loop for once, the here one loop, right? And you are doing that for how many times? 2 times, because R5 is loaded with 2 and R5 is actually running the loop. So that's why you multiply this with 2 and then the time taken for each machine cycle. So you get the total value. With all of this result, finally you can add these two outer instructions to get the total amount of time taken. So we have done that. Okay, so this total thing is actually written here after calculation, and with that this one and this one, these two are written here and here. Then you get the total amount of delay. That's all for this lecture. Thank you.